a total eclipse, instead of the sun being an extended object, it's this little slit-like, very point sourcey-like. Even though we're seeing little pieces of that edge of the sun, we can actually take a spectrum. Now here's a story some of you know and will be nodding off. I'm glad there are no desks in front of you. I won't hear your heads cracking on the desk as you fall asleep. For those of you who haven't heard it, right around the time of the Civil War, right after Bunsen, about 10 years after, they were doing spectroscopy of the sun, and they saw this emission line right here. And they looked through Bunsen's records, and they didn't find anything right at that wavelength here on Earth. They said, we found something on the sun that doesn't exist here on the Earth. Let's give it a name. We're good scientists. Let's see. Greek for sun is helios. We'll call it helium. Now you fast forward to right after the turn of the century. Some scientist, poor guy, his job was burning uranium. What a job. And his kids had 3 arms, I think. So he discovered as he burnt uranium, as Bunsen burned things, he saw the same exact color. And he said, probably not literally, Eureka, what we saw on the sun before that we thought was only there and we gave the name helium, we've now discovered on the Earth. So it's one of these great testimonies to how research gets done. And in this way, sort of backwards, we discovered something at a distance and then identified it here on Earth afterwards. Okay, other kinds of things. AVSO people study novae. Different novae have different shapes. A certain class of them, some 40 to 50% or so, have an iron emission line. Here Alain did, he's a Frenchman, on a Canon DSLR. He took this spectrum, plotted it here, was able to identify, also the characteristic shape of the curve would help, but was able to identify iron and help identify what he was looking at. Again, just very briefly, Doppler shift we all are familiar with. Doppler shift is the sound or pitch change that an ambulance makes or a train makes when it's coming towards you. I've got some pretty exciting slides here. I'm going to kneel down here, stay out of the way, and stop pacing a little bit. Here is a quasar. And in fact, before I show you the spectrum for this and interpret it, I want to be politically correct here. I think the hardware manufacturers benefit from us seeing gorgeous pictures in the magazines, even though many of us may never be able to attain those. It does act like a carrot, and it's a good carrot. It keeps us trying to do better. I don't think there's anybody misleading us deliberately. Think about when we all got into amateur astronomy. We wanted to see M31 in all its glory, or the Sombrero Galaxy. We saw these big posters. I want to see that, and we learned, well, we can't through an eyepiece. Can't even do particularly easily in imaging for some of us. What I'm showing you here isn't in those categories. What I'm showing you here was done on a 9-inch scope in the suburbs of London with a modified security camera with, I think it was like 10 minutes worth of exposures. So it wasn't 24-hour integration times like we see in the magazines sometimes. Here's the graph, and you'll notice there's 2 peaks here. Now, in the early 1960s, when the fundamental research was done, somebody a lot smarter than me said, those peaks, the distance between them across is about the same distance as the hydrogen bomber absorption lines that we saw in that Vega video inside of my software a minute ago. The only exception or difference is that they're in a different position. Now, if instead of saying they're in a different position, you heard me stumble there, if I said they're shifted to the right, that's the giveaway. Now, on a backyard scope, what we have just measured is the speed with which a quasar is moving away from the Earth. Now, this was in my article in Sky and Telescope, and Bob Noyer contacted me as a good editor and said, God, this is all on tape, I have to be careful. And he is a good editor. He said, Tom, in my write-up I said, this is Doppler shift. And so he contacted some astrophysicist, and he had an email that he shared with me. Basically, he said, and this is sort of longitudinal hair splitting. He said, Doppler shift is when things are moving. The Earth isn't moving in reference to this quasar. Space is expanding, so we don't call it Doppler shift. Okay, fine. So we're being more accurate in our language, and it was nice to have an editor who corrected me on that. This is now my favorite image in the show because of what we're about to do with it. This is a bright supernova. There aren't a lot of bright supernovas that we can capture easily with lower-end gear. This spectrum, there's the profile, was captured, again, to give you an idea what I was saying a moment ago about how you don't need high-end equipment. This is done with a C9, 9-inch scope. It's 30 25-second exposures. Now, a couple exciting things. First of all, this deep dip here is what astrophysicists use to identify this as a type 1a supernova. Now, I have a confession to make, and that is whether it's a Wolf-Rayet star or a type 1a supernova, I wouldn't have known 3 years ago either of those if they bit me on the butt. What's happened to me over the years, over the last several years, is when I get my hands on this kind of data, then I begin to have some hooks upon which to hang those things I've read about 3 or 4 times and have gone in one ear and out the other. So the learning that occurs, it's the same. Think back, for example. Think back to when you first, I guess I do have to take a breath now and then. When you first looked at M42, the Orion Nebula, maybe it was at a star party, maybe it was with your own telescope. For me, and again, maybe I'm a curmudgeon, for me, I went, it's a fuzzy cloud, so. But as we brought our understanding of what that was to mind over the years to come, that's when we became more and more fascinated with that image. Of course, we got better at capturing the image. But it's coupling what we're seeing and observing with what we understand. And it works both ways. Sometimes we see the thing and then we read about it. Sometimes we read about it or see somebody's research, and then we read about it to see, well, what is it that we've just observed? So for me, it's meant that I've learned. I've been pulled into learning, especially standing up in front of groups. But even at home, when I'm not giving a talk, doing some research on what people are telling me reveals a lot of interesting information which I'd otherwise forget. So here's just something that's absolutely startling to me. How fast is the shell of that supernova expanding? And we're going to calculate that. First of all, that dip there is ionized silicon, and it's bounded at 6150, right down there on the x-axis, angstroms. There's the absorption line in the actual spectrum. With a Bunsen burner or similar device, we could burn some silicon in the lab. It's not moving, and so it's stationary, and it's at that wavelength. We plug that into the Doppler shift formula, which, truth be told, I went out to Wikipedia and pulled up. I hadn't used it since high school. And we've now calculated the speed with which the shell of that supernova is expanding towards us. 22 million miles per hour. There should be 2 wows here. One is, wow, that's fast. The other is, wow, I can't believe I did this on an amateur telescope. 9-inch telescope, as I said. A few short exposures. David Strange is in the UK. He'd been using my software for about 2 weeks. So to me, in fact, I've shown this. I went, and I'll show you a slide in a second, but I can talk about it now. I went last year to the American Astrophysics Society. I did a poster there. You know, they have these long aisles filled with posters. And they're all postdocs, and they're all coming up to my booth, and I sort of felt like an imposter. I'm going, hey, golly, look what you can do. You know, and they're all, if they were military people, they're all senior postdocs. They'd have like all the medal and the epaulets, and they're just, and here I am saying, look what you can do. But they were responding slack-jawed too. They were going, oh my, I can't believe you can do that. I mean, these are people who use Hubble all the time, but whether they're professional or whether as us amateurs, it's not known just how easy it is to do this kind of thing. Now again, truth in advertising, this was a very bright supernova. We don't get that many. But this was also a fairly moderately sized telescope. It was a C9. So there actually was a second one subsequent to that that occurred in the last 6 months. I doubt it's a pattern of increasing supernovas given the nature of the world. But anyway, it's exciting to see the kinds of things we can do. We can classify supernovas. Here's the one that we just looked at, a similar one with a very deep absorption line. And that's a type 1a supernova. Here is a type 1 supernova, very different shape, so it has some hydrogen emission lines. Some other data we're not going to look at in detail. This we just looked at. This is another galaxy, 2 different galaxies and the kinds of things that we can observe. Now this is sort of interesting. Up until now, we've been looking at Vega-like stars, you know, some quasars and things, but this x-axis, if you look carefully, I need to issue opera glasses in my next talk for this kind of thing, we can see down to about 50 angstroms resolution. Anything that's thinner than 50 angstroms, any peak or dip, we just won't see it. It'll get lost. If you want to go down and look at that kind of detail, you can do that, but that's when you get into the slitted device. Now we're down to sub-angstrom resolution. This is Vega, which isn't moving with reference, oh no, excuse me, Vega is moving with reference to us, and the moon is more or less stationary in terms of radial velocity coming towards or away. So what we're seeing here is the Doppler shift because of the radial velocity of Vega. Now, the devil's in the details, as they say. Once you get down into this kind of resolution, you have to start correcting for the Earth's movement. As you know, if this is the sun and this is the Earth's coming towards you here and away from you here. So you have to subtract out that Doppler shift so that you see just the radial velocity Doppler shift of Vega. But this gets done all the time by amateurs. Now, you might ask, well, why don't I just start with the L-high-res 3? Well, first of all, there's plenty to learn with a low-resolution device. But more importantly, I have a quick story, and that is a friend of mine who went on to Microsoft, worked repairing Porsches in LA in the 70s. And he said on the wall of that Porsche factory was a sign. And I think that sign is not only with reference to Porsches, but just about everything. So a friend comes to you and says, what computer should I get? Or a friend comes to you and says, what kind of telescope should I get? Speed costs money. How fast do you want to go? You know, we all have, is it aperture envy, speed envy? We all want, you know, whatever it is. So when somebody says, what should I get? There's two questions. How dear is your money to you? And how fast do you want to go? So this kind of device is, again, in the $3,000 or $4,000 range. And I suppose I've never driven a Porsche. Are Porsches, has anybody driven a Porsche here ever? Are they, oh my God, a lot of us. Are they hard to drive or are they easy? Okay, so my example doesn't work. Darn. Ferraris are tough. Yeah, you can just break them loose, right? They have so much power. So anyway, this is high-resolution spectroscopy. This dip here is that dip here. There's plenty to be seen without going down to that resolution. A couple other examples, and then we'll look at how to get started, and we'll finish up. Spinning stars, if this is a big spinning star, if my head is the spinning star, this edge is coming towards you, and this edge, I can't keep my hands straight, this edge is going away from you, and this edge is coming towards you. So you get Doppler shift from the two edges, and that broadens, that's what this blue is, that broadens a dip. So this is how astrophysicists study this kind of stuff, is they look at what they expect to see, and Vega is a good benchmark milestone, it's relatively nearby and well known. That's what we expected it to look like, but it was really broadened. And so then they had to come up with the theoretical explanation for why that was happening. So here's how you get started. You need a diffraction grating. There's a variety of diffraction gratings on the market. Star Analyzer is the one that we've got. There's some reasons that we prefer the Star Analyzer over some of the others we can talk about if you're interested later. Any sort of camera. If you've got a camera today, that camera will work fine. Maybe a spacer, and you need some data reduction software. There's some freeware out there. That's the freeware I started with. This is my software. There's also some much higher-end software. But the software works with whatever camera you're using. So if you've got a camera today, you're good to go. I can never make this slide laugh, you know, or I can't make the audience laugh at this either. This is, anybody know the artist behind this? You'll be dating yourself. That's right. Oh, who said that? Somebody, yeah, somebody young. I know. I was going to say, I was expecting some of these old guys like me over here to know who it was. I mean, when I had hair to here, I knew who he was. So this is you. You got dressed up to come up here, I'm sure. This is me on a good hair day. And this is what people are doing in the field now. And I really, sometimes I feel this way. I just want to grab people and throttle them by the collar and go, look what they're doing. You know, why aren't you doing this? It's really exciting stuff. So anyway, just a little bit of autobiographical cartoonery. Let's look at some of the resources you have available. One is an interesting book for those of you who are do-it-yourselfers and like to build things. Ken Harrison's written a great book. You can buy it on Amazon. It's a little more hardware-oriented than I'd like. It's also a small format book. Let me just look at the time here. We're just about finishing up. He's coming out with another book right now. It's a helpful book. All this stuff is linked to on our site, and my email I'll be showing you here in a moment. You can always email me. I'm happy to answer any questions you've got. That's one great book. Another great book is, if my mouse would work, free book here that we can download from our site, and I've got that at my table over on Vendors Row, and I can show that to you. There's a variety of great sites. This is Kristen Will's site. There's some amateur pro-am collaboration going on the BESS or BE stars. BE stars, to refresh your memory, are type B stars with the emission line. And amateurs are gathering data. As with other observations that we do, we may not have big aperture on a per telescope basis, but we got a boatload of telescopes. And so we are contributing data to professional research. This is that AAS conference that I mentioned a few minutes ago I went to. This is Robin Leadbeater, and they're studying a BE star here. Christian Buell, I mentioned, is the CCD guy. Jeff Hopkins is in the US, and Robert Stenzel is the principal investigator at University of Colorado. German site, again, the web's your friend. There's plenty of sites on the web, and there's plenty of people who love to answer questions on a variety of Yahoo groups and other groups. So we've come a long ways in the last 50 minutes. Again, we talked a little bit about Fraunhofer, the father of spectroscopy, and this is a stamp that was issued in his name. You'll notice that it goes from red to blue instead of blue to red like the other spectra that I've been showing you. And we also talked about Kirchhoff in the middle of the 1800s, who did some of the research with Bunsen and also some of the theoretical underpinnings or underpinings of, which is it? Does somebody know? Underpinnings or underpinings? I've heard two different answers. Some of the basis of Bunsen's research came out of Kirchhoff's thinking. I'd like to thank you all very much for your time. Please come by the table at the vendor booth. I've got a telescope set up or a spectroscope set up to look at the sun. I think some of you guys are going to come over in a bit. And if you've got any questions, we've got a minute or two before the next talk starts.
Bob, real quick question.
Yeah.
You got like that supernova, that field of stars on your image. How do you zero in on
Great question.
area you want?
Yeah, the devil's in the details. If you have a star field with lots of stars, they're all going to be throwing spectra. And some of them are going to have spectra across, or some stars are going to be behind the spectrum that you're looking at. One thing you do is you rotate your grating to rotate the spectrum. Hopefully you can find a gap between them. And in fact, Jim here has been doing some of that. And you can talk to him after my talk or even watch him do some of it tonight. You rotate your grating and try and position the spectrum so it's not overlapping a star that's in the background. It's a great question, though. Other questions? Yes?
I have a spectrum question. Who coined the term, what they do on a Hubble telescope? They used to call it false colors.
Yes.
Who coined that term?
That I don't know. It's more of an imaging question than
Yes, but I'd like to punch him in the mouth. Because it's really a genius way of transforming
Yes.
Electromagnetic spectra into human
Yes.
objects.
Why would you punch a genius in the mouth? That's what I want to know.
Yeah.
It's a great way of doing things.
Yeah,
The
exactly.
nomenclature is wrong. I agree.
Well, that's why I'm going to punch him in the mouth.
Yeah. By the way, before I open it for Q&A, and we're just about done anyway, if you ask me many more questions, you'll discover just how broad yet not deep my knowledge is. There's some of you here who know a lot more about many of the subjects I've discussed, but I do know how to find answers, and hopefully all of you will help me find answers if you have questions I can't answer. Other questions? Yeah.
First of all, I have a color imaging source. Does that matter if it's color sort of mono?
Yeah, you can use a color camera. The only difference is with a color camera you have a little less sensitivity.
Okay, second thing was I have refractor. Does that matter as opposed to a reflector?
No, it depends. Depends on the telescope. Yeah, exactly. Yeah, and that we can talk a little bit offline. Yeah, pardon me?
We'll have to ask when you get
The refractor will work just fine.
Good. Other questions? That's it? Oh, and Bob here is also a user of my software. Thank you, Bob. And where's Jacob? Is he here? Oh, there he is. Jacob actually did some imaging of Saturn the other night with the grating, and I'm looking forward to seeing the results of it. All right, thank you all very much. Come by the table.